Alrighty, so one way we can classify materials. So materials can be classified by how compact they are. And what we call this is density. So it's a measure of how much mass is in a given volume. And the way we see that is with rho. This is a Greek letter, it's not a P. Just be very careful when you write it down on the AP test so they know what you're writing. I usually put a little loop in mine just so you can tell the difference. So we have rho equals M over V. This is your mass in kilograms. This is your volume in cubic meters. Let me switch that, volume. And if you've done this in chemistry or another science, they may give you it in different units. They're all still just mass over volume and you have to convert it. So our density is going to be measured in kilograms per cubic meter. Alrighty, so some examples of some densities. We've got water, and it's a nice round number. It's 1,000 kilograms per cubic meter. We've got air, and if you've taken chemistry, you'll notice what this STP stands for. That's standard temperature and pressure, so that's at 0 degrees Celsius and 1 atmosphere of pressure, and it has a density of about 1.29 kilograms per cubic meter. Let me switch markers here as that one's dying. Another one we've got is gold with a density of 19.3 times 10 to the third kilograms per cubic meter. And this one up here, I can rewrite it just so it's in the same times 10 to the third. It's just 1 times 10 to the third kilograms per cubic meter. And ethyl alcohol, which is the active ingredient in what we colloquially call alcohol, and it's 0.79 times 10 to the third kilograms per cubic meter. Notice this is still bigger than that one. This is times 10 to the third, so that's around 800 kilograms per cubic meter, which this one is still 1.29, which is significantly less. And when we combine this with the force of gravity, so this is combining with weight, which we write as F sub G, what we get is that, remembering back to AP Physics 1, we've got force of gravity is mass times acceleration. In this case, that's the acceleration due to gravity. When we plug in over here where we've got rho equals M over V, we can now rearrange this and plug in for M. So what we get is that the force of gravity, and this would just be for any type of liquid, the force of gravity is going to be equal to rho Vg, where rho times V, if we multiply by a V on both sides, we get V times rho equals mass. We plug that in here for mass, and we get this formula right there. And remember in this class that we are using 10 meters per second squared just to make our calculations easier. If you want to stick it out and stick with 9.81, you can do that. If not, 10 works for all of the AP questions. One cool property of density, which you've seen from the demos by now, is when something is less dense than the fluid it is in, it floats. So that only works when there's a downward force pulling the more dense thing down. But if you look at a hot air balloon, the air is less dense because it's hot, rises up. If you chuck a hunk of wood in water, it's got a bunch of air bubbles inside of it, which make it less dense than the water, so it floats up. Same idea. So instead of trying to memorize a bunch of densities, we found an easier way to do that, and it's what's called specific gravity. So in the case of specific gravity, what we're looking at is how something's density compares to that of water. So the specific gravity of a substance is going to be equal to the density of the substance over the density of water. So what I'm going to want you guys to do now is try to calculate the specific gravity for gold and the specific gravity for ethyl alcohol. Make sure you show your work. Pause the video right here, and right after this, the answers will be up on the board. So as you can see, the way I calculated the specific gravities here was to put the density of the object or the substance we're talking about on top, and then the density of water on the bottom. Thankfully, water is something nice and easy to divide by. It's just 1,000. So you just move the decimal point 3 places over on these, and you're good to go. An interesting fact about specific gravity, it tells you how much of a substance will go underwater if it does float. So if you notice here, it's less than 1. Things that are less than 1 are going to rise up because they're less dense than water. So if I were to drop some alcohol into water, it would only sink about 79% of it under the water's surface. So that is the usefulness. Why is specific gravity useful? It tells you the percent of an object that will sink. So technically, you could change the denominator and just make it whatever substance you're looking at, and then you'll automatically know how much of it'll sink. So imagine I threw an iron ball into a pool of mercury. It would tell me how much of the iron ball is sticking above floating. If you ever want to see a cool video, check that out. It really throws your mind off because you don't expect iron to float. One last thing I'm going to have you guys do is I want you to try using the density of air to estimate the mass of air in your room. And you can use if it was at STP because the density I've given you is lower than what it actually will be in your room, since it's it's higher because it's colder than what it is in your room, unless you're out there sitting in a freezing room. So go ahead and pause the video, try to do the calculations for that. I will tell you you're going to need to use the density formula that you got early on in the notes, and once you're done unpausing, then the answer will be up on the board. All right, so the way we did this here was I determined that the room was approximately 8.5 meters. This is the general shape of the room. 8.5 meters long way, and we got about a 2.5 meter section taken out here. And we have an 11 meter room this way, and we have about a 2 meter section taken out. So what I did was divide it into 2 squares, or 2 rectangles, I should say, and multiplied them together, knowing that the room is approximately 3 meters tall. So I did 8.5 times 9 meters times 3 to find the volume in this section. Then I did 6 meters times 2 meters times 3 meters to find out the volume in this section. Added them together and found out that the room is approximately 265.5 cubic meters. Now what I'm going to do is I am going to use the density of air at STP, which is about 1.29 kilograms per cubic meter. So density equals mass over volume. We're trying to solve for mass, so I'm going to rearrange this by multiplying by volume on both sides. I will get that rho V equals M. My rho is 1.29 kilograms per cubic meter times the volume, which is 265.5 cubic meters. Multiply them together. And I get an approximate volume of 342.5 kilograms. Now remember, this is going to be slightly higher than what we'd actually see because I'm not in a freezing room, as you can tell by the fact I'm in a short sleeve t-shirt. But this is a pretty good approximation. So as long as you can find out volume, you just multiply it by density and you can find any mass. One little addendum here. I want you guys to do a practice problem on specific gravity. So here we go. If I have a bottle and it has a mass of 35.00 grams when empty, and I'm going to fill it with water. So this is still the bottle. Filled with water, it has a mass of 98.44 grams. Now I fill it with a new fluid. So this is my mystery fluid. When it's filled with this fluid, it has a mass of 89.22 grams. I want you to try and determine what the specific gravity of the mystery fluid is. Go ahead and pause the video now, and when we come back, the explanation will be up on the board. All right, so what I've gone and done is I've found the mass of the water that's in the bottle, and I found the mass of the mystery fluid. And using that, I'm going to come up here and look at my specific gravity formula. Well, to find specific gravity, I need to know the density of my substance over the density of the water. All I'm given here, though, is my mass. So what I'm going to need to do is look at my density formula. What can I do with this to find my density? Well, we both know that the fluids are filling the bottle entirely, so they should have the same volume. So I can come up here and I can write that the mass of my substance over the volume of my substance divided by the mass of water over the volume of water. Since the volume of water is the same as the volume of the substance, I can cross those out, and all I'm left with is the mass of my substance over the mass of the water. So what I'll do is I'll put those numbers up here, 54.22 grams over 63.44 grams. And when I plug that in, 63.44, I get a specific gravity of approximately 0.855. So this substance would float in water. It would probably be just a little less dense than oil, and it would just sit right on the top of the water.